All right. Hello, everyone. Welcome back to a hopefully less stressful, environment. All is well, right? Logistics updates. Don't forget that you all have those like professional development activities that are kind of in the background. They're really straightforward. Reminder, the purpose of these, the reason I made them is to get you looking for outside opportunities. Motivate you to do so. As always, deadlines and tasks help us get things done. To-do lists, all that kind of jazz. So now just the purpose of these assignments was to give you a to-do list to find things outside of the classroom. Whether or not you do it, it won't affect your grade in any way, but it will affect your life, more importantly. So that's that. Otherwise, I started making your all's exam. And so to that end, the exam will be, at this time, here's the current plan, 3 free response questions that you'll pick 2 out of the 3 to complete. Each free response question will have a part A and a part B. So they will have kind of 2 parts to them. So 3 questions, each with its own part A and part B that go with that question. And you pick 2 out of these 3. The topics on the free response are about electric field, voltage. Electric field and voltage. So the free response will be about, currently the plan is 40% of your grade will be the free response. These more involved problems that have partial credit with the rubric that I need to post today or tomorrow. Did you draw a picture, write down what you're solving for, correct equations, all that kind of jazz. The other 60% will be some number of multiple choice. It'll be at least 20 questions, probably 25, something like that. You are going to have the full 2 hours and 50 minutes in here. Time will not be a concern for you all. You'll have plenty of time to check your work and all that. It's one of the blessings of the studio class. You will have plenty of time if you know you will have plenty of time. Also I need to remember, I got the note cards too. So at some point during class, I have note cards, so you can come on up and grab one of these at some point. We'll have our break and whatever, so it's a good time to do it then. Don't do it now. Just grab one, because I'll have them for future exams, but the problem is if everyone grabs 2, do the math. I have 400 students, 100 here, 300 in my other class. That's a lot of note cards as is. Multiply it by 2, and it's a lot of note cards. So I just need to make sure I have enough for each exam kind of thing. I do have whatever. So make sure, as far as the free response, the skills that I think are the most important and the most complex skills show up on the free response. Can you find the electric field? Remember, there's kind of 3 ways of doing electric field. One was the point charges and being able to add them up and vectors and all that good stuff. The other was the integration, Coulomb's law. Can you actually set up the integral for a continuous charge distribution? And the last was, can you do Gauss's law? Those are kind of the 3 techniques as far as electric field. Can you do those things? How do you know if you can do them? Problem set, quizzes. Make sure you practiced a bunch of those problems. Voltage. You need to make sure you can get the voltage due to point charges. You need to make sure you can get the voltage due to an electric field. You're like, well, how do I do that? Remember, there's the integral. V equals the negative integral of E dot dl. Can you do that integral? One of those skills of building the integrals is a skill that I'm really trying to support you all in, because it's a useful skill that you all need to be able to do. And then the last part of voltage is, can you do those conservation of energy problems? Do you know how to do those? Remember, there's a few of those in the problem set and all that good stuff. So those are the ones that are going to show up in the free response. The multiple choice will have a smattering of, kind of everything. And those ones, the multiple choice, I expect it at most to take 3 minutes for a problem, at most. So those will be a mixture of pretty straightforward problems or conceptual ones that it's based on pictures and drawing things and stuff like that. Resistors will be it. We'll learn about resistors a little bit today, and we'll finish it up on Thursday. Capacitors, all that kind of stuff, those will show up in the multiple choice. So capacitors, yes, they'll be in the exam and the multiple choice. Resistors, on the exam in the multiple choice. So the electric field voltage will also be in the multiple choice, but it will be the only thing in the free response. No capacitors, no resistors in the free response.
Are the problem sets our most reliable study guide?
Yeah, it's a great question. Are the problem sets the most reliable study guide? Yes, but also make sure you're doing the clicker. So basically your things to study are the problem sets, the quiz problems, and then the clicker problems, the iClicker problems. So the iClicker problems represent the conceptual problems that I've been doing. So when I make this test, I look at all of these things to determine what kinds of questions I can ask you on a test. And the test then will be variations. Nothing on the test will be like a one-to-one necessarily. They'll all be kind of variations. They're all written differently. None of them are word for word the same. So the problem set's not going to have a ton of conceptual, but the iClickers are like all conceptual. Things that you can do without a calculator, basically. The problem sets then are practicing the numerical and the plugging in things and stuff that takes a little bit more time. But yeah, rule of thumb, multiple choice, you should be able to get done in 3 minutes or less. The free response, my thought process is like 15 minutes for an entire problem, part A and part B. You will have way more time than that to do these things. You'll have time to check your work, get into the Blessing Studio, all that good stuff. But that is currently the plan, and currently the plan in process. And we'll have a review day next Tuesday, but we'll very easily finish all the content. All right, joke of the day.
Hello, everyone. I got some wisdom for you. Build a man a fire, and he'll be warm for a day. Set a man on fire, and he'll be warm for the rest of his life.
Yeah.
It's true.
Yeah, it's good. I'd say good. It's a yeah. Anywho, capacitors. So last class, the things we talked about the dielectric. We talked about the dielectric. The electric field is a constant, but by putting a dielectric, you can add more charge, and boom, we increase the capacitance, dielectric constant, all that good jazz. And then we spent a decent amount of time trying to understand series and parallel. So remember, in series, they have the same charge, but their voltage drops add to give you the total voltage drop. In parallel, they have the same voltage drop. That was the definition of parallel. They have the same voltage drop, but they each have a different amount of charge on them. And we finished there. We practiced finding voltage, which ones are in parallel, and we saw they were all in parallel. So good. And then we derived how to add them together. And I promised you all that I'd explain why we're adding them together. What's the reason for this? Why are we taking two capacitors and turning them into one? What's the value of this? And so that's going to be shown today when we solve a problem. So by solving a problem, we're going to see why this is valuable. And I can kind of actually show you all here very briefly. So this was how to add them in parallel. So remember, they get the same voltage drop. So let's call this capacitor up here capacitor 1. Let's call the one down here capacitor 2. Let's say the one down here has charge 2. Let's see the one here has charge 1. Based on this circuit, well, okay, this one's actually pretty straightforward. It's easier to show it. Let me actually go to the series one, because this one is actually a little too trivial. In the series circuit, where's that one at? There it is. No, that's the derivation. All right. So let's say this is 5 volts. This is 0 volts. This is capacitance 1, capacitance 2, capacitance 3. Let's say this is charge 1, charge 2, charge 3. And they all get the same charge. So we'll put that as Q, Q, Q. Voltage 1, voltage 2, voltage 3. So if I gave you this problem and I said, find how much charge capacitor 1 has on it. And I would give you the capacitance of capacitor 1. And I'd give you the capacitors, I'd give you the voltage, drop across the whole thing, and I say, find the charge on capacitor 1. Here's the problem. All right, great. I look at capacitor 1. Hey, I've got the capacitance. Yay. I don't know the voltage. Well, I don't know the charge, and I don't know the voltage. I can't solve it. You cannot solve a problem with two unknowns. So, C equals Q over V. So rearranging this, if I want Q, I need V. Like, what are you going to do? There's no other options. So, well, if we combine them into one, I know its capacitance. And I know its voltage. If I have one capacitor in a circuit, the only thing in the circuit in this picture, what's the voltage drop across it? It's 5. It starts at 5, it ends at 0. How much does it drop? 5. Hey, look, I got C, I got V, I can solve for Q. And if I know Q of this one, I can work backwards. The Q of this one is the same as the Q of the other ones. So that's a lot of words. Let's actually just do it. So for now, just trust me that this is valuable. And here's the problem where I've got some capacitors and a whole bunch of systems here. And your goal is to your first goal, turn this into one capacitor. And then and the second goal is what is the charge in each capacitor? And the last is what's the voltage in each capacitor. But let's just focus on A right now. What is the capacitance of, if I want to turn this into one capacitor, what is the value of that capacitor? I need to turn this into one capacitor with a voltage drop across a 5. Why? Because that's the voltage in the problem. And here's my hint to you all. I'm kind of just going to cut you loose and try this. Remember, you can only combine things if they're in series, completely in series, and you can only combine things if they're in parallel. If there's some combination of both, find ones that are just in series or just in parallel, combine those, make a new circuit, and then go from there. So that still might have been too much information, still might have been confusing. First question to y'all. In this circuit, there are two capacitors that are either purely in series or purely in parallel. I'm not going to tell you which. I want you to find those. There's two capacitors that are either purely in series or purely in parallel. I need you to find where those are. And that's your first step. Find the two capacitors that are either purely in series or purely in parallel. Those are the first ones we're going to combine. The variable C is capacitor.
I think that works. What are you talking about? Yeah, I assume we're gonna.
So as far as voltage is concerned, basically what we need to remember is a wire. Everyone on the wire is the same height. Until it takes a capacitor or so like here, this blue wire.
I think that's what he said. We're going to set up.
Why? Here's the wire split. 5 and 11.
Oh,
This one's purple one. Everyone on this wire is single.
I just cut one out.
Because the wires don't change voltage. Yep, just did the wire split. Because over here you weren't concerned that it split. So why should you be concerned that it split over here? Yeah. So then, you look for some that have the same starting and ending. And something that's helpful when you're doing this is drawing where the voltage is the same. Remember, voltage is the same everywhere on a wire. Voltage only changes once you hit a capacitor. After you go across that capacitor, then it's going to change. Or a battery or a resistor. If y'all remember the color coding back here. We don't care that the wire splits. We don't care that the wire splits. The voltage is everywhere along that wire. Who cares if the wire splits? When does it change? When you go across these capacitors. So that's as far as parallel. Series, we have to look, is there any such that I can go from one to the other without, there's no alternative paths. So let's look for series first. If we kind of look at this first one, so we're going to start here. All right, the wire split, but let's just look at this one. Is anything in series with this one? I should be able to go from this one to another one without running into a junction. A junction is a fancy name for where it splits. So I'm going up, I hit a junction. Nothing's in series with it. Why? Because the path split. Series means one after the other. All right, so that one's not in series with anything. Let's look at this one. All right, I go from this one. I hit another junction. And if I go the other way, I hit a junction. There's no way to get from that capacitor to any other. So that one's not in series with any. So none of them are in series with each other. Why? Because there's junctions between every single capacitor. There's multiple paths in between them. None of them are one after the other. There is no single path I can take from one capacitor to the other. There's always these branching paths. All right, so then we draw this voltage. It's 5 volts everywhere where I drew it red. Why? Because it's just a wire. I don't care that the wire split. It's the same everywhere. This one, I'm going to draw this one. It's the same voltage everywhere on this blue thing. I don't know what that voltage is. We'll just call it like V1. I don't know what it is. I don't need to know what it is for parallel. And then we have our last little thing. The voltage here at the end, that one is 0 volts. So series we ruled out. Are there any capacitors here that start with the same color and end with the same color? Yeah, which ones? The first two. These are in parallel. Those two are in parallel. Do they physically look like they're in parallel? No, but they are. And this is something I wanted to challenge you to understand, is that parallel doesn't mean physically parallel. Parallel means they have the same voltage on both sides. This circuit is the exact same thing as this circuit. This is often how it would be drawn in maybe some other physics classes. These are the exact same thing. Putting the capacitor on the top of that branch or on the side of it doesn't change anything. I mean, when you build this circuit, you don't need to build these wires you're not actually like bending these wires at right angles to make it look like this. When you physically build these things, the wire's, gonna bend and loop. Like, who knows what that wire's gonna do? You don't care. It doesn't change anything. So this is the same as this, is the same as, if I decided to put it over here. All three of these circuits are the exact same thing. Where it's at on the wire doesn't change anything as long as it's not relative to other capacitors changing. All right, so great. What I need you all to do now, combine these two capacitors. We need to take this, and we're going to combine them, and I need you all to draw what the new circuit's going to look like when I combine them into one. I'm combining these, and I'm not touching anything else in the circuit. See if you can draw the picture what the new one looks like. We'll start with 5 volts. We'll end with 0 volts. We're not touching. This guy's not getting touched. What's the rest of the circuit going to look like when I take those two and I smash them into one capacitor? And find the value of it.
Yeah. Voltage before and after both capacitors are the same. Yep. The only thing that's different is the charge.
Yes. Yep. Perfect. Yeah. It looks like you. 9. But then they won't add nicely. 1 over 3 plus 1 over 6 will not equal 1 over 9. Yeah, denominators don't add nicely. Yeah, you got to go through the math. Yeah.
Is the one thing you got first time? Oh, yeah. Is it?
Oh, they're in here, yeah.
How do you have
Is
oh, sorry, it isn't. I like it, isn't it? Yeah. No, I like you, it isn't. Yeah. In parallel, you just add. I saw the 1 over thing and I forgot.
Do you have to also include that? Like
That one didn't get touched. Yep, so there, yep, it's just there. We haven't touched that one
But
yet.
if you were simplifying it, then you
We are going to. Yeah, we are. That's the next step. Yeah.
remembering.
Yeah, that's a perfect drawing. How do you add capacitors in parallel? Yep. Who's that? This is 9. Yeah, 3 plus 6 is 9. 3 plus 6 is 9. Yeah, so that's the unit for capacitance. If you bought a capacitor from the store, that's what we do.
Yeah.
It's its capacity to store charge. That's the unit for.
Yeah.
All right, so you combine them into one. We take these two, we smash them together. Boom! There's one resistor. There's one capacitor now. It turned into one capacitor. Now, how do I add these? Oh, and something that's kind of helpful is you could like label this 1, 2, 3. You don't have to, but it's just useful. So I would like call this capacitor 1, 2. Why? Because 1 and 2 together. Just kind of nice notation. How do y'all add capacitors in parallel? What's the technique? Is it the inverse or just add them? You just add them. Easy peasy. C1 plus C2, which equals 9 microfarad. I've got this question a few times, so that means it's good to mention. Farads is the unit for capacitance. It's its capacity, its ability to store charge. That's what capacitance is. If you went to an Ace Hardware and you bought a capacitor, it'd be listed as microfarads, nanofarads, millifarads. It's how much charge you can store in it per volt. All right, now hopefully y'all can look at this and tell what kind is this. Is this in series or parallel? Add them in series. Turn them into 1. And right now you're like, why am I doing this? All will be revealed. There's a reason. There's a practical reason for this. Is it good?
I think so.
Oh, you don't need to hook it up to a battery.
To measure it?
Yeah.
Really?
Yeah. This will supply its own voltage.
Oh,
I don't exactly.
yeah.
But no, you just poke into it. Yeah. This is very useful because if you're diagnosing a failed capacitor, you just take it out of the circuit.
That does help.
And you're going to go to the lowest value. All the way down.
Yeah.
It goes higher.
Just like this with the paper, right?
It should work. It should work. Try different multimeters. Also make sure this one's as fast as possible. But yeah, it should read for you. So try bigger sheets.
Okay.
That's yeah. Try bigger sheets. Okay. It worked for my one at home, so that's how like this should work. Yes. All right, so we turn it into 1. How do I add capacitors in parallel? What's the strat? Do I just add them? No. 1 over C net will equal 1 over C12 plus 1 over C3. I'm leaving the variable form just so you can see what I'm going to do. C12. So this ends up being, this means that C net is going to be 1 over 9. And you're going to be like, he didn't put the units in there. The answer is going to have microfarads just tacked onto it. So if you want, you can put the e to the minus 6. Or you can realize at the end, I'm just going to get the e to the minus 6. All right, so 1 divided by 9 plus 1 divided by 4. So I get 2.77 microfarad. Yay! That was the answer to part A. What's the equivalent capacitance? Now, the question is, why did we do this? What was the point? Well, part B says find the charge stored on every capacitor, C1, C2, C3. And then part C is what's the voltage across C1, C2, C3? If you really want to, you could try to figure that out from this picture in the beginning, but good luck. You're going to have to do some mental gymnastics. Why? In the beginning picture, do you all know the voltage drop across capacitor 1? So I know it's capacitance. I want to solve for V and I want to solve for Q. Do I know the voltage drop across this? No. Do I know the charge on it? No. It is, again, there's some mental gymnastics you could go through, but you have to really know what you're doing to kind of do it. Can't do that here. But let's look at this one that we just made, this nice single capacitor. With a capacitance, so let's call this C123. Why do I call it that? Because it was capacitor 1, 2, 3 together. Again, it's just convenient notation. It's fairly straightforward what it's representing. Hey, I know it's capacitance. What's the voltage drop across it? Based on my nice picture here, if it's the only capacitor in the circuit and it's 5 on one end and 0 on the other, what's the voltage drop across it? 5. This means I can solve for Q. I can finally start solving for some things. You're like, but that's not what the problem asked. The problem didn't ask me for the net one. For now, trust the process. Solve for the total charge on this one capacitor. Fairly straightforward. I'm not going to tell you the equation. I think you can figure it out. If not, someone around you, I'm sure, will know the equation. Find the charge on this net capacitor. I tested it. I know this is feasible.
How big was your piece of aluminum?
I did like a tiny little piece.
Really?
Mm-hmm. That's very sad. Let's make sure that this does measure capacity on here.
Yeah.
Well, sometimes there's different plugs for these things. Mine was in the same plug, so. Yeah, you're definitely in the right spot, for sure. Alright, it's gonna start creating right now. I'm like, yeah, I think if you do there, I don't know how they would have gotten broken. Grab like 5. Let's rule out that because I tested it with a cheap
yours
one.
works then.
Cheapo deep, like way less nice than that. It had just one capacitor.
Like flat it more, do you think, or?
Mine had one capacitor setting. That was it.
Test it again.
Oh yeah. It's not working at all.
All right, so hopefully you realize what's the magic equation. If I want to get Q, what am I going to do? C equals Q over V. If I rearrange that, Q equals C times V. Easy, just multiply them together. 2.77 times 5. I'm going to get 13.84 microcoulombs. Straightforward. So what? Why do we do this? Now we can start going backwards. Now we can start going backwards. When we go backwards, these resistors that we did up here in the top right, are they in series or parallel? What's the same in series? Well, I'm hearing different answers. What a good opportunity for a clicker question. What's the same in series for capacitors? Voltage, charge, nothing. This is a very important rule that you'll need to know to do this problem. Give you 40 seconds.
It's not even measuring capacity on this side.
Okay. So there's no, which one are you using? This one's way.
I tried this one.
You're using it on the highest So what's weird is it doesn't show you.
Like we did try all 3 of them, but we didn't increase it.
So I'm really wondering if you have to
I was thinking about that too.
I'm thinking that you might
This is like special.
it shows some wires.
Oh,
It sounds stupid, but like you just need contact. My best guess is you're gonna have to do that. This is the temperature profile. These normally would just tell you. So this is voltage, frequency, resistance. This one says oh. So go ahead and shove some wires in there.
So they need to connect.
They just need 2 wires, positive and negative. They should fit. So as long as they can make contact. All right, 5, 4, 3, 2, 1. Pachow. All right, it is what it is. There's not much to say about this. It's charge. There's a whole slide we did on this. We chatted about it. Feel free to go back and look at it. Why does this matter? We know the charge on this one. Charge in series is the same. So if the net capacitor has this charge, then each of the capacitors up here has that charge. So, just to kind of write this out, the Q for this capacitor, let's call this one, this was C12, Q12, V12. Q12 is 13.84 microcoulomb. Q3, 13.84 microcoulomb. All I did was put the same number there. Oh, look, I know 2 out of the 3 things. So guess what you can solve for now? You can solve for voltage now. And then you can take the one that splits into 2 and take the thing that's the same and try the same step. This is the technique for these circuits. Turn it into one capacitor, get all 3 values, Q, V, C, and then go backwards. Whatever stays the same, stays the same. In series, charge stays the same. Take that back a step. If you're going back and it's parallel, voltage stays the same. This is why we needed to combine it into one. We didn't have enough information to begin with. Now we do. Slowly but surely.
So V1 is the same as V5. Right? Like for the parallel thing, like it's the same voltage.
Oh, V is some. So we can figure out what it is. Once you figure out V1, 2.
Yeah, but it's not V. It's a different number than V5. It goes down.
Oh, yeah.
Okay.
You can figure out how much it goes down. When you solve for V1, 2, the voltage drop across 1 and 2.
And that voltage drop.
Yeah, that's one I
That was
And I was even I
And
was
that
like
would mean that whatever voltage you start with here, it's going to drop that much.
Yeah.
Is it working?
Do this. We think it's giving us numbers, but they're
1 means it's too high.
yeah. It's like it's going all over the place.
So you just keep going up.
Is it really that much?
I also find it hard to believe.
Like it'll show some numbers and then just randomly go away. I'm trying not to like touch it or move too much, but it's also hard with these. If they make contact, would it screen up?
Oh, it's going to speed things up a lot.
Yeah. So.
Here, take a big sheet of paper.
Yeah.
It will ruin everything because it's short.
Right. That's what I was figuring.
My best guess is this is finding the time constant.
There we go. Thanks.
Think about it conceptually.
Nice.
If the voltage is the same,
Okay. That works now. Just make sure they don't touch. Makes sense.
So now you actually find a fire.
all the boxes have them.
Oh, they do?
Do you think there's any like actual specific thing to put in there?
I'm sure there is. Do I have it?
Dude, no.
Good luck.
I guess we'll just get a bunch of wire. Do we have wire strippers? Because these are long.
Stockroom probably does.
Sure, check.
All right, so you all should find the voltage for those. How do you find the voltage? It's just Q over C. V equals Q over C. So the voltage is going to be 13.84 divided by 9. So that's going to be 1.54 volts. And we're going to see something really cool here. You're like, what do you... Physics, cool. No way. 3.46 volts. What happens if you add 1.54 to 3.46? What number does that turn into? It's 5 because it's the total voltage drop. Look, it all works. This voltage plus this voltage equals 5. Why? Because there's 5 across the whole thing. Isn't that nice? So nice. All right, so then you all just need to go back one more step. And you all need to find the voltage and the capacitance, the voltage and the charge on these two guys here. The 3 microfarad and the 6 microfarad. To do that, you go backwards, and we're going to take this capacitor. When I go backwards, series or parallel? Parallel. What stays constant when you go backwards and it's parallel? So take the voltage value of 1.54. That goes to this one. That goes to both of them. They both get that nice 1.54. Solve for charge, and then you're done. So this is the magic, and we're going to be doing this with resistors after test 1. They have a different, their rules are flipped, but it's the same process, just flipped rules. And I'll put the answers so that you know when you have it. It's a little ugly, but it's there.
What was the question again?
Find the charge and voltage on the first two.
Two. So.
The end goal is to find the charge and voltage in every single capacitor. Yep, everyone's got their own charge, their own voltage, their own capacitance. Do it for the 3 microfarad capacitor, then do it for the 6 microfarad. The end goal was find the capacitance, charge, and voltage for every single thing. I'll make a pretty little table.
Oh, it's rounded up. Because the answer is 4.62. Rounded. 4.62
All right, so there's a nice, easier to read table with all the answers. The capacitance, the charge, and the voltage of every single capacitor. They would need those stripped anyway for future labs, so it's fine. You're doing a service. But each of these boxes has this long... Okay.
I'm hoping that they have a bunch. Do you think I don't know how much light to give them.
Strip more than less. Huh?
Is that enough?
Oh, so I keep each box independent and just strip the wires long enough to fit in the holes.
Okay.
If that makes sense.
Oh, so like don't
So don't
shorten the
make
wire?
No. Keep the wires nice and long.
Okay.
Each box has their own long wire.
Gotcha.
So I'll just grab them.
Oh yeah, here you go.
I'll just come around.
All right, so this is the end of capacitors. Yay, this is everything you need to know about capacitors. Now we'll start doing stuff with current and resistance. So we'll jump to the next PowerPoint, kind of slide on that. Current and resistance is going to be fairly straightforward. I mean, yeah, capacitors, this is probably the trickiest thing in it. But once you can do one of these, they're all this, combine them all together, then work your way backwards. I'll tell you on the test, if I gave I'd only give like one of these as a multiple choice if it showed up. And I wouldn't even go all the way. I wouldn't say find. Remember, any multiple choice needs to be doable in 3 minutes. So obviously this took us longer than 3 minutes. But I could ask you the net capacitance. That'd be really simple. I could ask you, hey, I have 2 capacitors shown in the following circuit. What's the same on both capacitors? Stuff like that. Do you know about series? Do you know about parallel? All that good stuff. All right, so on to current and resistance. In our lab for today, if you're like, what have the TAs been doing? They are building a lab. So your lab today will be building capacitors with aluminum foil and paper. And you're like, what? That sounds weird. What is a capacitor but 2 infinite plates separated by an insulator? Aluminum foil is a nice plate. Build 2 of them, put a dielectric between it and a paper. And then our multimeters can measure capacitance. So you'll be able to determine theoretically what the capacitance should be. You can measure its area, distance, all that fun stuff. And then you'll actually measure what it is experimentally. And that's, if you're like, what are they doing? They're cutting aluminum foil and they're making the multimeters work.
You can keep that.
Uh,
I'm sorry.
so,
Keep that. That's a good idea.
all right.
This one. Oh, this is the big one.
No, we're doing it before.
Yeah.
They're making
All right, so while they continue to work on that, let's learn about current, which we've already talked about a bunch. It's the flow of charges. And we'll see, so we're probably going to get through a decent amount of this. Something that's nice with this class, I'm like an hour, 20 minutes ahead in this class compared to my lecture class. And content-wise, the test is going to be similar for both. So anyway, we might end up covering a few extra things that might get shoved up, but it'll be like the very end, the very, very end. So my goal with you all, at least, is to get through what is current, what is resistance, how is resistance calculated geometrically, and how does resistance vary based on temperature. That's kind of the three major goals of this PowerPoint. What is current? Oh, and Ohm's law. Introduce Ohm's law. It's very simple. We're not going to do anything crazy with it, but at least to see it. If we can get to power, that'd be great, but we'll see. So, some things you all need to remember when we're starting to slowly get more and more into circuits. You need to remember that electrons are the ones that can move, not protons. You need to know what voltage is, and that voltage is the same as potential difference. Voltage, potential difference, electric potential. These are three words that say three phrases that mean the exact same thing. Why do we have three different phrases? I have no clue why, but we do. Same exact thing. And you need to remember about electric potential energy when we eventually derive the energy that is transformed in a circuit. The power, what we'll end up learning. Super, super practical stuff here, like capacitors, resistors, learning how to use a multimeter. Every single one of you will benefit from this as long as you don't shy away from it. Having a multimeter is an incredibly useful device at home. I have used this to fix my sprinkler system. I've used this to fix my AC system. I've used this to fix my refrigerator. Not because I have a vast amount of knowledge, but because a lot of fixes are really easy. A lot of fixes are, is there a short in my wire? Multimeters can determine whether there's a conducting path. Your AC unit, it's just one capacitor. It's really easy to change. Your refrigerator, there's actually only, there's this relay. I had to determine whether the relay was broken. How? I measured its resistance. How? Multimeter. So if you have a sprinkler system, you also have these solenoid valves. You can measure the resistance. So many applications. So many applications. You can save yourself a lot of money and diagnose things yourself. If you're an engineer, you all are going into STEM fields. This is something you should be able to do. If you can, it's okay. But what is an engineer? What is a computer scientist? What are all these people but a problem solver? And if you have a problem with the thing at home, can you fix it? You all have the ability to, if you don't know it, you can learn it. But I'm going to teach you that if you don't know what voltage, current, resistance, capacitance is, it's going to be harder. So I'm teaching you kind of the theory, practical-wise, watch some YouTube videos. They'll have you measure the right things, but you actually know what you're measuring. Unlike most people where they're like, it gives me a number. What is resistance? I don't know. All right. So we're going to learn what current is. We're going to very briefly talk about how batteries generate current, but not in any, this isn't a chemistry class. Talk about resistance, Ohm's law, and then power, which is how much energy is converted per second. So this is the analogy I like to give people. I'll give you all a few moments to think about this. I got a table with a bunch of marbles on it. How can you easily make them all roll in one direction at one time really easily? Think about it, chat about it, give you all 30 seconds, and then I'll hear what your ideas are. I'll hop around and hear the ideas. That's just like the fun.
Yeah. Engineering.
They can do it.
Alright, it's 10 megabytes. We're like halfway there.
And then you also have to do like pieces which have those.
Right. Yeah, I already did that.
Nice.
So why don't you? Yeah. I'm blowing away from my time, but I guess every group needs one of these boxes now, right?
Yes.
I think they're all four should be all good to go. I don't know if I actually need a filter. I was saying that in case there wasn't enough wires for everybody.
Well, we could say that if you're having trouble getting like, the end of your wire in
Then
there,
all it would be
come
nice
over
to
us
have,
and we'll
yeah,
strip it.
just in case.
But we should not hand that out.
Oh, man.
Double major, just double major.
All grayed out.
I should have said a lot.
All right, great. What are the strats? I've got 2 people. They got it. So how do I make this thing start rolling? I tilted. What did you do when you tilted it? What variable? We made a height difference. Now, if I take this whole table and I increase the height everywhere on this table, oh man, I lifted the whole thing up. Is anything going to happen? No. If you increase the voltage everywhere, the height everywhere, nothing's going to happen. It's not about making the voltage higher. It's about making one end higher than the other. It's about making a potential difference. Anytime we talk about voltage, we don't care what the voltage is. We care about the difference in voltage between 2 points. The bigger that difference, the faster they're going to roll. And what is this rolling? That's going to be current. The rolling balls, that's current. A wire is filled with electrons all the time. There's electrons in every single piece of metal. They're there. They're inside of it, everywhere inside of it. So the second you apply this voltage, it's as if this pipe is filled with water. A wire is kind of like a pipe filled with water. When I tilt it, all of it starts moving at instantaneous. Technically, the information takes the speed of light to reach it, but effectively, every single one starts at once. It's not like when you add a battery that it pushes one, which pushes one, which no. They all they experience that voltage difference all like instantaneously. You don't need them to run into each other. No one told me that I need to push and then push and then push and then push and then push. No. Just tilt it. They all start moving at the same time. All right. Positive voltage on the left. 0 voltage on the right. Which way will charges move? And what charges will move? Will it be positive charges? Will they move to the right? Positive charges to the left? Negative charges to the right? Negative charges to the left? Yeah.
I was doing that at first, but
Whatever, I was like, because you're going to, the stripping of the wires, that's what's going to probably take you the longest.
yeah, I think they're all good.
Oh, really? They got
I
long
was
enough
thinking
charge?
that. Well, I mean, if any aren't, I'll have it, which is nice. But I was thinking that if there wasn't enough wire to like cut it and strip it, just so that everybody has to play some, you know.
Okay.
But I think we're good.
Yeah, as long as I'm just worried as long as I can reach inside that thing.
Yeah.
It's a little bit of a jinx. There should be a probe, but a probe.
Yeah, ours worked really
Yeah, when you
pretty
asked
easily.
them, they said that they didn't have it.
No.
Like, it's apparently come up before.
That's fine. Shoving wires in there is the same thing as a probe.
Right. MacGyver.
Yeah.
And MacGyver.
Same charge. So
Is it the negative charges move left? Is it protons that move?
I've got it.
kind of like.
It would be alright.
You can have a positive, like, you're only putting electrons for negative
All right, 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, so to answer this question, we need to understand what an atom looks like. Why? Positive charges. What particles make positive charges? Protons, electrons, or neutrons? Protons. Where do I find those positive charges? Where are they located in my atom? The outside, the nucleus, and the outside, where are they at? They're out in the nucleus. So, we're going to draw a nice pretty cloud here. So, if you tell me that positive charges are moving, you're telling me one of two things. Either you're ripping protons from the nucleus, which is fission, which means you're doing a fission reaction. Kind of crazy. Or you're taking the entire atom and moving the entire atom. If you have a copper wire, that would mean you're taking copper atoms and literally moving them in the wire. You can also see that that doesn't quite sound right. Now the electrons, where are those located in a conductor? The sea of electrons. This free space. So the negative charges are going to move. And do negative charges move in the way we expect or opposite the way we expect? Do they move uphill or downhill? They move uphill. Negative charges do the opposite of, because it's like positive mass does what you expect. Positive charges do what you expect. Negative charges always do the opposite. So, negative charges are going to move this way. Now, why am I telling you this? Current is defined the other direction. So this is the thing that's weird, but what I wanted to convey you all, what's the reality? What is actually happening in a wire? Negative charges are moving. It just so happens when they discovered, invented, whatever phrase you want to use for this current, this flow of charges, they didn't know what was actually happening. This is a long time ago. They didn't, maybe understand all the details. So they decided, and I think this is Benjamin Franklin's fault, he decided that current goes in the direction of positive charges, which is the opposite direction. Why do I tell you this? Mathematically, it changes nothing. When you're doing the math, this changes nothing whether or not you define the directions one way or the other. What I am trying to convey to you all, though, is that the reality is opposite. So when I'm about to tell you that current goes from high voltage to low voltage, that doesn't mean that particles are moving from high voltage to low voltage. It's actually the opposite. But mathematically, negative charges to the left is the exact same thing as positive charges to the right. Mathematically, it's the same thing. Doesn't matter. So, boom, here's the definition of current. It's the rate at which positive charge flows. It's dq over dt. How much charge per how much second? It's defined as positive charge moving. The reality is negative charges are moving the opposite direction. So the reality is opposite. 1 amp equals 1 coulomb through some area per second. And this current is constant. We chatted about that. Remember in series, the flow is the same everywhere. Throughout a wire, the current is constant unless there's an alternative path. Unless there's another way you can go. And I'll chat about that last point and just give you all another analogy for helping understand that. And let's show a nice little simulation so you can see what I mean by they're opposite, but it doesn't matter. All right, so this idea of current being constant through a wire, this is when you're in series. Unless there's an alternative path, that means a junction. We'll chat about those eventually. We've already mentioned them a few times. So my analogy to you all, I've given a few already, given you the one with water, but here's another one. If you're on a 1-lane highway, 1-lane road, and the semi-truck in front of you is going 20 miles per hour, Guess how fast you can go. 20 miles per hour. I don't care how fancy your car is. The max you can go is the speed of the semi-truck behind, like in front of you. So in a wire, I don't care if that wire bends. I don't care what the wire is doing. As long as there's no other road for you to take, you're going to go the same rate as everyone else in that road. Imagine bumper to bumper to bumper traffic. That's these electrons in the wire. Where they can't go faster than the ones in front of them. Everything's kind of going the same rate. Regardless of what they're passing through, whether the road's bumpy or smooth or whatever, every point, you're kind of going the same on that. All right. Here's a pretty picture. Let me pull up in this simulation. I've showed you all this a few times. Well, let me close my email so nothing pops up there that shouldn't pop up. Go away. All right. So I mentioned to you all this before. There's this FET simulation. I love it so much because you all can't see electricity. You can see arcing and things like that, but no one can see the electrons moving through a wire. Just, I can't. If you can, good on you. But we're going to take these resistors. We're going to take some wires, a battery. A battery is providing that voltage difference. And so this is just a simple circuit. It's as simple as it gets. So right now, you all can see those negative charges moving, and they're moving from that high voltage. They're going from the low to the high. This is the positive terminal of the battery. This is the negative terminal. This is low voltage. This is high voltage. The electrons are fundamentally going. This is what's actually happening. This is what's physically happening in a circuit. If I then change it to conventional current, it goes the other way. It's not the reality, but mathematically it works out the same. Doesn't change anything as far as your all's problem solving or anything like that, but this is just a useful fun fact for you all to know. Anyway. All right, so, charge flows. Yay! Okay. I have the utmost confidence in your ability to solve this. How much current flows through a wire if 30 coulombs of charge passes through it in 2 minutes? Is it 15 amps, 1.5 amps, 0.25 amps, 0.4 amps? There's only one right answer. Check with your group members. Think about it. That's my hint to you all. Take your time. Always base units. What do y'all think? That's really all this is testing. Yeah. It's a good question. We always, any equation that you always use base units. This is just saying your way. Alright, y'all figure it out?
When the last one was counted, how many?
It's 77. I'm about to be done. There's just one more of these.
All right, 20 more seconds. If you caught it, you caught it. This is more just a wake check than anything. All right, and 5, 4, 3, 2, 1. So yeah, the definition of current is dq dt, but if it's a constant rate of flow, we can just replace that with delta. So how much charge? 30. How much time? 2 times 60. Convert it to seconds. You're like, whoa, why do you multiply by? Everyone I chatted with, I think, caught this. That's why I kind of just jumped through it. Base units, seconds. Don't forget that. Every equation I give you is calibrated for base units. We got to all be speaking the same language. So we need to convert our units to base units anytime. Unless you want to report your answer as some weird answer, some other unit. So nice work, nice work. All right, great. Try this one out. It looks gross, but it's really not bad. If you think about what, so let's read through it. Current through a conductor is modeled as I of t equals I naught cosine 2 pi 60 hertz t. Write an equation for the charge as a function of time. So I've only given you all one equation in this PowerPoint. Probably going to use that. Think through it. See how you would kind of rehash things. The fact that it has the 60 hertz in there, just pretend like it says 60, it doesn't really matter. I wrote it that way. That's not signifying anything.
Where's the other paper?
Oh, yeah, but it's not.
Yeah. Gotcha.
If they don't, we have the paper over there. All right, so
We're gonna need one of these for everybody down.
yeah, and they're all under here. Yeah, it's so weird that they have the different.
I guess we'll have to explain this part. Trash. This is all trash. Thank you.
So when you plug it in, yes.
And now we can get the side. Oh, the right side turns into
Yeah,
the left side. You do. Let's go. You'll figure out how to do it. What's the relationship between? There's only one relationship. So let's write it out. Yeah. So show me the let's write it on variables first. So the equation was I. Let's write that out. Alright, y'all figure it out? Wait, solve for Q. Solve you want Q, right? Take Q by itself. So write it, take Q by itself, and then I'll show it. So rearrange that for DQ. I want to get that total Q. So I have an infinite amount of PQ, then I add them all up. Sides. Integrate both sides. Integrate the right side. Integrate the left side. Alright, so if you haven't figured it out, so we're solving for Q. There is only one equation I've given you at this time. So that's usually a hint, that's one we're going to use, but how else would you know, oh, I've got I want Q, what's the relationship between them? Then you just rearrange this. So we're going to do something that physicists like to do that mathematicians don't like to do. We're going to multiply the dt to the other side, which I don't know why this is a faux pas in math, but I always, other physics, when I was learning these things, I always constantly heard people say that. So for some reason, I think mathematicians don't like this. I don't know. We do this all the time in physics. Great. Well, if I want the total Q, I need to add them all up. How do I add up all the Q's? Integrate both sides. If I integrate the dq, what does it turn into? Q. And what does the right side turn into? I don't know. Do the integral. Just chuck it on in there. It's a pretty easy integral. There's no bounds of this integral at this time, so just you'll add a constant at the end, that's fine.
Not all boxes of 2 wires.
Yeah, so I was afraid of that. There's going to be...
You said you can't like cut any of the really long ones.
I mean, we can if we have to.
Yeah.
I always just hesitate cutting wires because
So
obviously
you can't uncut
you
it.
can't uncut them.
That's
So,
true.
and it's really nice having
I
long
guess-
wires.
Yeah, I guess last resort.
But yeah, if they don't have them, we don't need long wires. For this, you really only need wires like this long.
Yeah, that's
Oh,
what
I
I
thought
think.
you were talking something else. I heard science, not I.
All right, so the integral of cosine is sine. So we get I naught times sine of 2 pi times 60 times t, all divided by 2 pi times 60, because if you took the derivative of this, it should have spit out a 2 pi 60. Where did it go? Oh, it canceled out with the bottom. That's how I actually do integrals. I think of what derivative, what function, if I took the derivative, would give me this. That's what U sub does. Plus c. And that's it. That's the answer. So great. This is just helpful to remind you all that if it's a derivative, you can do backwards too. If I gave you the function for charge, great, take the derivative of it to get the current. If I give you the function, and this is going to be very relevant when we get to RC circuits. This will be something we cover after test 1. RC circuits, charging, and yada, yada, yada. We'll get to it when we get to it, but this will be useful then. So it is relevant. It is important for electrical engineers and things of the such. All right, cool. I'm really not, so previously I was kind of excited to cover charge density. I'm really not going to spend too much time on it. It's not a big deal. There's a couple problems in the problem set. I'm just going to tell you now, I'm not going to test you on charge density. Current density. It's really easy though. Like I'm going to chat about it like 5 minutes and just whip through it. Current density is so easy. You just take the current and divide it by the area. It's just like charge density. It's how much current flows through this area. This is something very important. The reason I wanted to spend the time on this is if you're building circuits, physics majors, electrical engineer majors, you generally might care about the current density, how the current is spread out, more than you would actually care about the total current. Sometimes you actually want to know how the charge is distributed more so. It gives you more resolution, gives you more information. So that's why I mentioned it here. Physicists love it. When we talk about Maxwell's equations, you don't actually see current, but you do see current density. Just to show how easy this is, yes, I'm going to have you all do this question. I have the utmost confidence in your ability to do it. A current I passes through a circular wire with a radius of R, assuming a uniform current density. What is that current density across that cross-sectional area? You can see it in the picture. Is it 2 pi R I? This is an I, not an L. I know it looks like an L. It's really unfortunate that Arial, the I, looks like an L. It's kind of a pain. Those are all I's. So 2 pi R I divided by 2 pi R, I pi R squared, or I divided by pi R squared. Which one it would give me the current density in this thing?
Not a bunch.
Oh, that up. That looks awful. It's that ugly.
Cut a little bit.
Yeah, no one's using that. No one's using that for anything. And we really only need pieces like
I found like some like these.
this long. Oh yeah.
But
Yeah,
this is gonna be like really big fast.
Yeah, as long as the piece is like this big.
Gotcha. Oh, it's like-
Yeah. Deal with it. Let's see if we need
Yeah. Wow.
I don't know about that.
I guess plug it right. Right? Give it a long.
Yeah, I do a little more down it.
All right, I'll give you all 20 more seconds.
Oh yeah. That one kind of sucks. This one might be easier to.
No, yeah. It's too high or too low.
I'm gonna, you're the only thing. Now.
That one's really hard. Without chopping it in half.
But the reality is,
No, it's just true.
You're all set. Everyone varies.
It's so satisfying when you get a
Right.
clean cut.
You wanna do it all?
Yeah, I made it so far.
Every now and then it happens, but all right, 5, 4, 3, 2, 1. All right, so yeah, it's just the current per area. What's the area that it's pass? It's the area that it's passing through. It's drawn in the picture. How pretty? It's just I over pi r squared. That's it. Like, this is me just showing you it's really simple. If it's uniform, yay. If it was non-uniform and I asked you for the total current, you could integrate it, but not really because it's a double integral. So here's a pretty little slide on it that I'm not going to actually ask you all any questions about current density, but I am mentioning it because it's very relevant for physics majors and electrical engineers. It's what you want it to be. It's I over A. It's just what you did. If the current varied, you do a partial derivative with respect to area. That's the fancier one. It could vary. It very likely will vary. So, yay, there it is. One last quick thing, and then we'll take our break, is one question that probably didn't come to your mind. Maybe it did, maybe it didn't. How fast do these charges move? Like, are these charges moving super quick in a wire? Are they moving slowly, quickly? I don't know. Maybe something you never thought about. You got electricity. You might have known it was a flow of charges. Are they flowing fast? Are they flowing slow? Like how, I don't know, their electrons are pretty small. It feels like they could go really quick. But for them to go really far, like they're really tiny. They'd have to be going really fast. I don't know. It's an interesting question. So this is a quick derivation on that. You don't need to know any of this. It's just kind of a fun little thing that's pretty straightforward. So, okay, look, that's boring. Let's actually derive it. So, again, I'm not going to actually have you all do this in any capacity. It's just a fun little 2-3 minute thing based on stuff we learned. So, the total charge is the number of electrons, that's N, times the area of it, times the length, times the Q. So you're like, what, why? I'm just counting up the number of electrons. I'm multiplying a number of electrons by volume. What's area times length? That's volume. So basically, this is how many free electrons per meter cubed. Actually, I should put that here. Number of free electrons per meter cubed. So I am multiplying this number times volume times the charge of each electron. Nothing fancy. How many electrons do I have? Multiplied by the charge of an electron. That's my total charge. Hopefully that lands. All right. Current is defined as dq dt. So you can see that down here. Velocity we can also define as distance divided by time. Like just if it's a constant velocity, that's true. So by plugging it in, so I equals dq dt. We then plug in what Q is. NALQ over dt. N is a constant. A is a constant. L is a constant. Okay, well, kind of, sort of. Q is they are constants, but based on that definition, we're doing some kind of hand wavy-ish kind of stuff here. The length it travels per unit time, that's velocity. So if I rewrite this over here to the side, the number of electrons, that charge density, that's a constant. My area is a constant. But these things are moving. So the length they travel per second, that's basically the only thing inside the integral. So it's just dl dt. What is dl dt? Oh, that's velocity. That's how fast they're going. That's the whole point of this, is we're figuring out how fast they're going. So long story short, we get that the current equals N times A times Q times V. All right, why is this relevant? This means if I know the current, I can figure out how fast they're going. That's it. You just rearrange this. And the only thing that's kind of funky here is you'd have to know how many free electrons you have. And so you have to kind of maybe do some weird, you have to say like, imagine it's copper. Say each copper atom has 1 free electron. How many copper atoms are there per meter cubed? You'd have to do some like density and Avogadro's number and whatever to figure this out. But you figure out how many electrons you have per meter cubed by just how many atoms you have and how they're spread out. And you end up finding the velocity is less than a millimeter a second. It's just kind of a fun fact. This flow of charges, they're moving really slow. And why are they moving really slow? This is relevant. They run into things. It's not like a free path. You have to think about these things traveling through it. There's literally atoms in the way. You can almost imagine, you know those like Plinko boards where like you jump a bunch of things and there's all the little pegs that they bounce off of and they eventually make it to the bottom? It's just like that. They don't have a straight path down. There's atoms in the way that they bounce off of, but they're constantly getting pushed through it. So yeah, it's almost exactly like those little Plinko board things. Yeah, but it's kind of slow. It's interesting, but there's a lot of them. There's a lot of these charges, so the net result is great and interesting. Cool. So we're not really worried about this problem. Next class, we'll get to resistivity. But we're going to go ahead, take a break. Then we'll go ahead and start setting up for the lab. So during the break, if you want to sign up for your groups, great. Remember, max of 3 people. You cannot have 4. Also, remember, at your table, you can only have 3 groups maximum because we don't have enough equipment for more groups than that. You got there 3 little flags, 3 computers. You know, it's all there. 3 max people, 3 max groups per table. And then if you want a note card, you know it's up here. If I run out of those, I got more. Don't worry. Just grab only 1, please, unless you're grabbing it for a friend. Then that's fine.